As the core of DNA sequencing discrete rapidly, whole genome sequencing technique is generating data at an unprecedented scale. The number of studied individual sequence increased from 1,000 to hundreds of thousands and even more. For example, the project in Precision Medicine Initiatives program, scientists are being challenged to manage whole genome sequencing data that are terabyte size and diverse type of data and complex data relationship. Data analysis of whole genome sequencing require a general file format for storing genetics variant. The variant code format, VCF, is a genetics and flexible format for storing DNA polymorphism, which was developed for the 1,000 Genome project. It is the standard format in use today. However, VCF files are large, and the computational burden with large-scale data retrieval from text file is significant. As the number of individuals increase to tens of thousands or even more, the need is for a flexible and high-performance data format to store and analyze variant data become essential. JSeqArray file format stores variant data in an array-oriented members, which provide the same capability as VCF, but with high compression option and data access using high-performance parallel computing. JSeqArray is originally implemented in a bytecode package with a highly optimized C++ kernel. The detail of this new file format and the performance comparison has been published in my recent bioinformatics paper. Here I introduce a new Xiuwen package for data manipulation of JSeqArray file. So table 1 lists the key function provided in this package. Many data analysis can be done using just this function. The function CFilterSet and CGetData are used together to retrieve data from a subset of sample and variant. The function CApply applies a user-defined function to the array margin of genotype and annotation. The last function, cParallel, utilizes the built-in parallel functionality in Xiuwen to perform calculation on a JSeqArray file. Let me show you the script. At first, load the JSeqArray package after you install the package from GitHub. CExample is used to get the file name of example data, and COpen to open the file. The hierarchical structure of the example file is shown in the output. And the variable name indicates the functionality. For example, the sample ID, variant ID, genotype, and annotation. Each variable name is followed by the information of data type, dimension, compression algorithm, and storage site. You can see there are 1,092 individuals in this small example file. We use CGetData to retrieve data from the file with a given variable name. Here are sample ID, variant ID, and position. The sample and variant ID could be either string or integer. Position are always integer. If the data file is too large, it is not feasible to load all data into memory. We need to define a data subset with a filter of sample and variant. For example, we select the first 4 sample and the first 6 variant as a data subset by the function CFilterSet. And then we get the genotype just in that subset. Genotype is a 3-dimensional array with products, sample, and variant. 0 in the genotype array is the reference allele. 1 denotes for the first alternative allele. And you can see we use 255 as a missing value. Another useful array is the dosage matrix representing the dosage of reference allele. For example, the number 2 in the matrix indicates there are 2 copies of reference allele at a site of human genome. The pound sign in the variable name indicates that this variable is not actually stored in the file, but it actually is calculated from other variable. Next, we can call C filter reset to remove any filter on the data set. Okay. Let me show you how the function CApply works. There are 2 major dimensions in the data set, sample and variant. Here is a array data set we are working on, which consists of 20,000 sample and 200 million variant. The data set is quite large. It is not possible to load all genotype into memory. We load the genotype in chunks and patch each subset of genotype to the user-defined function, blocking the calculation. Here is an example for the calculation of allele frequency. In the user-defined function, the input variable genome is a 3-dimensional array of A-bit unsigned integer. This function calculates the frequency of 0 in the genotype array for each variant, and it returns a vector of floating number. The keyword argument S is equal to unless indicates flattening the return vector. Next. In the example of principal component analysis, we initialize the covariance matrix at the beginning, and then we use the function CApply. The user-defined function calculates the allele frequency, normalize the dosage matrix, impute missing value, and update the covariance matrix. Finally, we scale the covariance matrix by the sample size and the trait of that matrix. The output is a scaled covariance matrix. We conduct eigen decomposition on this matrix. The figure shows you the first and second eigenvector. That is a top 2 principal component. The study individuals have different color according to their ethnic groups. The function CParallel automatically splits the dataset into multiple non-overlapping parts according to different processes. Since the sample size is much smaller than the number of variants, we split the variant dimension only, as shown in the figure. Okay, we launched 4 worker processes in Xiuwen. You can use more. Actually, we usually, for this large data set, actually we usually use a 100 computing node. We need to provide a user-defined function to CParallel. The first argument of the user-defined function is a JSeqArray file object, which is open in each process internally. The body of function is the same as the previous slide to calculate the covariance matrix. The keyword argument combined is a process to end up the result from the worker process together. So finally, we get the same PCA figure as previous slide. So any question?